5 into 10 to the power minus 2 kilogram of kilogram lump of clay that is moving at velocity 10 meters per second in a horizontal direction to the left strikes a 6 into 10 to the power minus 2 kilogram lump of clay moving in the same horizontal direction to the right at velocity 12 meters per second. All right, now this is interesting. Who's okay? This is moving to the right. So one clay lump is moving to the right, and the other clay lump is moving to the left. All right. So yeah, 5 into 10 to the power minus 2 kilogram clay lump that is moving at a velocity 10 meters per second horizontal direction to the left. Okay, this is 5 into 10 to the power minus 2 kilogram, and it is moving at a velocity of 10 meters per second. And the other one moving at 12 meters per second, and it has a mass of 6 into 10 to the power minus 2 kilogram. This is what's happening. The two lumps stick together after they collide. Now, this is just before the collision, and just after the collision, they stick together. So it means there is 11 into 10 to the power minus 2 kilogram. The composite object will move at velocity of, right? So luckily they have asked only the magnitude of the velocity. They have not asked for the direction, but you need to figure out the direction first of all, people. You need to figure out the direction first of all. So for this one, if you find the momentum here, momentum mv, I'll just put mv, momentum of this one, that will be 6 into 10 to the power minus 2 multiplied by the velocity 12, and that is 72 kilogram. So sorry, 72 into 10 to the power minus 2 kilograms per meters a second minus 1 towards right. All right, and here if you take the momentum, it is 5 into 10 to the power minus 2 multiplied by 10, and that is 50 into 10 to the power minus 2 kilograms meter per second. Kilograms meter per second, and that is to the left. So as you can see, initially the momentum towards right is more, it's greater than momentum towards left. Therefore, the resultant momentum also has to be towards right, and that's the final velocity. So sometimes you have to figure out the direction based on the magnitudes of momentum. And since the momentum towards right is larger, the resulting momentum also should be towards right, right? So what do we do? Final linear momentum equals to initial linear momentum. Final linear momentum is the total mass multiplied by the final velocity. Initial linear momentum should be written as, we have already found them. So 72 into 10 to the power minus 2. Remember, I'm choosing this direction. Why? Finally, it's moving to the right now, people. Right. Minus 50 into 10 to the power minus 2. Right, we are almost there. Now, when you get when you have 10 to the power minus 2 everywhere, you can get rid of that. So finally, velocity, here we have 11v. On the right side, I have 22. Therefore, velocity will be equal to 2 ms minus 1. 2 ms minus 1. So the answer for this question is third. Even if you have marked the velocity opposite in the opposite direction, still you will get the correct answer, but with a negative sign for v. So no problem there. The next question is from 2003, and let's see what it says. Two boys of identical masses are standing on two identical trolleys, A and B, which are at rest on a frictionless horizontal surface. So this is a smooth surface, no friction here, okay? The boy on trolley A then throws a ball of mass simple m horizontally with velocity v with respect to the earth, and the boy on trolley B is capital M. There is, I think there's some information missing here. If you check the original paper, this boy catches the ball. This boy who is at rest. Okay, he has the ball, and then he throws the ball and he catches the ball. And then they are asking what are the final velocities, and they have marked v in this direction, and probably they are taking right side as positive direction and left side as negative direction. Positive and negative, right? Fine. So let's see what happens. I might have to draw another separate diagram to analyze this. First of all, the boy inside trolley A, he has the ball. So let's start from one corner. He has the ball in his hand as well. He has the ball in his hand, and the mass of the ball is simple M. So the mass of the ball is simple M. Mass of the boy with the trolley is capital M. This is how it is. And okay, the other boy, I'll just draw him. He's at rest. He's not doing anything. And then this is the first step, right? Everything is at rest. Zero momentum in the whole system. Zero momentum in the whole system. And then something's happening here. I'll draw that in a separate color so that you will be able to understand it clearer. This boy is throwing the ball away from him. Throwing the ball away like this. Right? And the ball has a velocity of v. It moves like it goes away from him. And the mass of the ball is simple M. Mass of him is capital M. Right? So initially, you can see there was no momentum, and suddenly, and this is a smooth surface, so the trolley is quite free to move around anywhere. Okay, quite free to move. There's nothing to stop the trolley. So when this boy throws the ball away, what's going to happen? There is a sudden momentum created towards right side. But mind you, the boy B, this is B and A. He's not doing anything. He's just minding his own business here. So that's why I'm drawing that in blue color. The black color is where the action happens. All right. So to balance out this momentum, the trolley and the boy should have moved to the left. I'll take it as VA, the velocity of A with the trolley. Okay, hope you understood. Here both are at rest, and then you suddenly throw the ball to the right. Then to balance out that momentum, the trolley should have moved to the left. Okay, right. So for that situation, if you apply the equation, you can say for this situation now, final linear momentum towards right towards right equals initial linear momentum. Since they're asking for the trolley, the velocity of the boys, let's take it in that direction, right? Equals to initial linear momentum. Initial linear momentum, right? So what is the final linear momentum in that direction? That is going to be capital MVA minus simple MV. Why did I put minus? Because the ball is going to the right. And initial linear momentum, when you compare these two situations, there's nothing. Okay, right. So I'll be getting MVA equals simple MV, and VA is actually equal to simple MV divided by capital M. Remember, the direction is to the left. To the left is the direction. All right. And look at the answers. There are negative answers. So definitely the trolley moving to the left, therefore they have taken it as minus. So VA is minus MV over capital M. Right? So we have that answer in 1, 2, 2. So first and third. Therefore, second or fourth or fifth definitely not going to be the answers. We have to eliminate as many answers as possible and improve the probability of getting the answer correct. So we have to choose between first and third. All right, fine. It's only about the sign. Everything is same except for the sign. But anyways, for our clarity, I'll try to get the answer also. Now what happens is, after this, A will keep moving to the left. A will keep moving to the left at that velocity of VA. So he's gone now. He'll be gone. But now the other side will be in action. What's going to happen? This ball, simple M, is moving at V towards the other boy, and he's trying to catch it. He's going to catch it now. He hasn't caught it. He's going to catch it now. He's waiting like this. He's going to catch it. And this is B, but his initial velocity is 0. He has not caught it yet. Once he catches it, what will happen once he catches it? Now he has caught the ball. What will happen? Along with the ball, the system will now move to the right. And that will be velocity B. Why is the system moving to the right? Because there is a momentum now. There is no momentum in this system. Suddenly when he catches it, he catches the momentum of the ball also along with him. Therefore, the entire system has to move to the right to balance out this momentum. Hope you all understood that. All right. Now, there's no connection between A and the ball because ball has left A. Now, ball is moving towards B. Before B catches the ball has a momentum. Now, once he catches the ball and the boy are together now. Simple M, capital M are together. Therefore, the system should move to the right because before the ball was caught, the system had a momentum towards right. All right, let's finish this off. So what should we do now? Final linear momentum towards right should be equal to initial linear momentum towards right. Everything is moving to the right. That's why I'm considering that. Right. What is the final linear momentum towards right? That is going to be capital M plus simple M into VB. Why capital M plus simple M? The reason is both the man with the trolley and the ball, the system, are moving together. Equal to the initial linear momentum is MV because point to the right. And finally, we will end up in an equation like this. VB is equal to MV divided by capital M plus simple M towards right. Towards right. Yeah, so right and left directions are important because momentum is a vector. Therefore, the answer should be the third one. Both can't be minus. If both are minus, what is the meaning? Both are moving in the same direction, but it doesn't happen that way. All right. So this is like a collision. The object is initially, the whole system is at rest, and suddenly two momenta are created. And this is like a bullet getting embedded into a wooden block. Bullet will travel towards a wooden block, then the bullet and the block will move together. But all of this is possible because the surface is smooth, so there's nothing to stop the trolleys from moving. Two boys, A and B, standing on a horizontal ice surface, move apart by pushing each other. So when they say horizontal ice surface, you should understand the fact that this surface is smooth. There is no friction, frictionless. Frictionless. All right, fine. So initially, I'll just draw them as boxes like this. Huh? A and B, they are pushing each other. Initially, they both are at rest. U equal to 0, U equal to 0 on the smooth surface. Once they push and they start moving apart, what will happen? A will be moving backwards like this, and B will be moving backwards. So I will draw it like this. This is just of okay. Yeah, this is where they were. Okay, I'll draw it down. Then it's easier for us to compare, right? So now, once they push each other apart, then they were here initially, both like this. They were at this point, and once they push each other, what will happen? A will move backwards, and what have they mentioned about their masses? The weight of A is twice that of B. The weight of A is twice that of B. And A would have moved, A will move some distance with a velocity. I'll take it as VA. And B will move with another velocity. I'll take it as VB. All right. So they will be moving at constant velocity. The velocity will not reduce because the surface is smooth. All right. If there is friction, then their velocities would have reduced. But whatever the velocity at which they left from each other, left away from each other, they will keep moving in that. It's a hypothetical situation. We will, right, fine. Hypothetical situation. In reality, it doesn't happen because there will be a friction for some extent in reality. You have resistance and everything within a human error. Right, fine. So they are comparing between the distances. Now, what are they saying? Okay, by the time A has moved 4 meters, right? So A has moved 4 meters means this is 4 meters. They are asking what is the distance moved by B. What is the distance moved by B? So I'll take it as distance B. And if they started here when time is equal to 0, both should have traveled same time, na? Both should have traveled same time. Both should have traveled same time. Right. So first of all, final linear momentum equal to initial linear momentum. That's easy. Quickly, let's finish it off. Right. Let's choose a direction, maybe to the right. So what is the direction to the right? Momentum to the right. That will be V. Okay, wait a minute. A mass of A is twice that of B. So let's take the mass of B as M. Therefore, mass of A should be 2M. Right. Final linear momentum should be MVB minus 2MVA. Initial linear momentum is 0 because both the men were at rest. So VB is equal to MVB is equal to MVA. Therefore, VB is equal to 2VA. So this person will be traveling at double the speed of A, right? Both the what both the men would have traveled the same distance. So if the velocity of B is twice that of A, that means the distance covered by B should be twice that of A. So SB should be equal to 8 meters. You can directly compare velocity and